Okay.
Brilliant, brilliant. Okay, let's start. All the bearing manufacturers together make 10 million bearings a day. Now that's the total world production. The vast majority of all bearings produced survive the application in which they have been applied. However, there are still 0.5% which fail prematurely and therefore do not achieve their optimal lifespan. Here we see 4 main reasons for premature bearing dropout. About 16% are lost by the hammer and chisel mechanic, incorrect actions before the bearings even turned, suffering damage and thus early failure. We also see 34% early failures due to fatigue, to the wrong type of bearing in the application, or over time, the user demanding more from the bearing, greater speed, greater load, etc. We should also be aware that at least half of all premature fatigue failures, that's this 34%, are due to alignment errors. An alignment error indicates imbalance, an imbalance gives overload, and an overload, of course, also gives early fatigue and failure. We also see that more than 30% of failures are due to incorrect lubrication, which is more than a third of all premature outages. Incorrect lubrication, too much, too little, or the wrong lubricant. Count on top of that 14% by contamination. Contamination from outside due to improperly selected seals, but also initial contamination during assembly, grinding and welding particles, and even when relubricating. There's a high potential risk of contamination. We should maintain it properly so we keep the contamination out. With sufficient attention to lubrication and maintenance, you avoid 50% of premature bearing outages. That's more than half of the outages due to lubrication. So, what is lubrication? It is whatever creates a barrier that reduces friction between two contacting surfaces. This barrier may be one of various media in frictional order, starting from the lowest, gas, in other words, which includes magnetic, anything basically that in that case you don't have any material or metal to metal contact at all. It just sits in a gas bubble. Next one would be air, also with air, but with oil in mist or drop form. Next, oil, which is various types: hydrostatic, hydrodynamic, forced flow, bath. Then comes grease, and lastly, dry or solid. This webinar is mostly concerned with grease lubrication, as SKF has a presence in most of these lubrication types, but as we do not have sufficient time to do justice to all of them in this webinar, we should just be focusing on grease. So why lubricate? Primarily for separating the bearing surfaces, thus preventing wear and reducing friction. This reduces heat and flushes out particles to lessen secondary wear, as the particles act as a grinding paste to generate further consequential damage. Number two, secondary, but also they're important, we lubricate to protect the bearing against corrosion and against external contaminants. We can therefore say that the lubrication acts with the seals to provide an umbrella for the bearing. When a bearing is properly lubricated and maintained, there are relatively low costs. Now, compare this to the high impact of a bearing failing, causing an unplanned, i.e. expensive, stoppage. High repair costs, consequential costs such as damage to shaft and or housing, and of course the purchase of new bearing. It can even lead to unsafe or dangerous situations, i.e. in an aircraft landing gear, in an elevator, an escalator and so on. That's where people's lives are at stake. Appropriate maintenance and lubrication is clearly a good investment. However, despite this, lubrication is often too much, too little, wrong lubrication, and the wrong lubricant with questionable cleanliness. Only a partially effective sealing and debatable grease storage and documentation. The importance of proper lubrication and maintenance suggests lubrication management as a basis of operation. Now, how does a good lubricant work? I mentioned earlier the need to create a barrier, separate the surfaces and avoid metal-to-metal contact. We know that even with water, this is achievable when we are driving in our car at high speed through a large puddle. It is called aquaplaning, as you lose contact with the road and nullify any control the brakes may have. Generally not a good idea if you value your life and even more importantly your car, but at least you have discovered lubrication. You will have discovered, or perhaps remember from your school science lessons, the difference between a gas and a liquid. Gases are compressible, liquids are not. This means that if you load up a liquid, it will tend to displace itself, move out the way. But during that nanosecond between action and effect, it will support the load. That is why aquaplaning tends to work better at speed. Windsurfing is Windsurfing is a more positive and beneficial aquaplaning example. In a rolling element, the process of utilising this property is referred to as elasto-hydrodynamic lubrication. All a bit of a mouthful, so from now on we shall just call it EHL. In the rotating bearing, wave formation occurs in the lubricant. That much of a mouthful, I've had to take a drink. In the rotating bearing, wave formation occurs in the lubricant and elastic deformations of rolling elements and raceways arise. These flat areas, such as a car tyre, form the contact surfaces that we need to build a lubrication film. We are talking about extremely high pressures of up to 40,000 megapascals in the contact surfaces of the bearing. As well as incompressibility, the other requirement for a good lubricating oil is something called viscosity. So what is viscosity? Viscosity is often described as the thickness or thinness of a liquid. It is highly temperature dependent and values are usually quoted at temperatures of 40 and 100 degrees centigrade. Now water, for example, has a very low viscosity of 1 millimeter squared per second, which is more commonly called centistokes. So they're the units, millimeters squared per second, but usually referred to as centistokes. Now that's at 40 degrees centigrade. Honey, on the other hand, is much more viscous than water, and at 40 degrees centigrade has a viscosity of at least 1200 centistokes. All viscosity tends to reduce their temperature rise to 100 degrees centigrade to typically a figure of perhaps a tenth of the value for 40 degrees centigrade. So 100 centistokes, say for instance at 40 degrees centigrade, will be about 10 centistokes at 100 degrees centigrade. That's the ratio. This ratio is normally shown in logarithmic form. You might well have seen it in the various charts, and it's called the viscosity index. Of course, when the water converts to this, it does tend to lubricate pretty well. But I digress. That's just another type of lubrication, which we won't be talking about too much in this webinar. You may also remember from your science lessons, or at least well I do, the teacher demonstrating viscosity by filling long thin tubes with different fluids then inverting them and measuring the quantity retained by the fluid's surface tension remaining in the tube. This directly relates to why viscosity is so important to EHL, why speed and temperature is so important to the process. Because the oil needs to adhere to the bearing surfaces for long enough for the process to work. Obviously, the higher the viscosity, the higher the speed, and lower the temperature, the easier it will be for the oil to stay in the contact and for a pressure wedge to form. If the speed and stroke or the viscosity is too low, it cannot form. Now, viscosity, isoviscosity classes. When we talk about speed in any calculation, we mean linear speed. We convert it to linear speed, which is normally millimeters per minute rather than RPM. To do this, we multiply the shaft or wheel speed in RPM by the mean bearing diameter, which is the outside diameter plus bore, divided by 2, to get something we in the bearing industry typically call an NDM factor. By doing this, we can see that a large bearing rotating at slow speed, such as this, that's a large spherical, and if that's rotating at slow speed, may require the same viscosity to achieve surface separation as a small bearing, such as that small deep groove ball bearing, running at high speed, which it often does. So it's not that sort of necessarily that simple, just looking at the speed. You need to look at the bearing size and the bearing type as well. Also, of course, a given bearing size operate at high speed, but also high temperature, may require the same viscosity if operating at low speed with correspondingly low temperatures. So that's an interesting one. That means that, say, for instance, a bearing running at high speed and generating the sort of temperature that would be resulting from that sort of high speed may actually require the same sort of viscosity as one that's at slow speed and generating no temperature at all. A lot of calculation required, but you'll no doubt be relieved to know that there is no time during this webinar to go into this detail. For those curious to know more about this subject, please refer to the SKF General Catalogue pages 88 to 103, and also the lubrication chapter. It's all good bedtime reading. Otherwise, at least take away from the webinar the following rule. Now, I think I will just sort of repeat this. High NDM, think low viscosity rating. Low NDM, think high viscosity rating. Low temperature, think low viscosity rating. High temperature, think high viscosity rating. So if you want to make a note of that, so it's high NDM, low viscosity, low NDM, high viscosity, low temperature, low viscosity, high temperature, high viscosity. All viscosity ratings or classes are set by international standard, ISO, as shown in the table. So it goes from ISO VG2 right up to 1500. As a rule of thumb, small, very high speed bearings, i.e. machine tools, tend to use ISO VG22 or lower. So that's 2 to 22. My background's in pumps and other fluid machinery devices, which in my experience tend to use ISO VG 3268. So it's that middle range, 32 to 68. And ISO VG 100 and above tends to be used for gearboxes and large, heavily loaded, slow movement, etc. Lubrication film buildup. So provided we know the bearing size and speed, we can calculate viscosity required to achieve EHL. And also, provided we know the oil grade and temperature, we can also calculate the viscosity achieved by the by the lubricant. So we've got two things. We've got viscosity required for an application and viscosity achieved by the lubricant. Now, dividing the viscosity achieved by the viscosity required, we get the viscosity ratio kappa, as shown here, K. Kappa should ideally always be greater than 1.0. However, if it is much greater, or up to 4, or greater than 4, we get uncomfortably close to the aquaplane example shown earlier, where the rolling elements slide rather than roll, thus risking premature failure from cage damage as the rolling set moves out of control. However, less than 1, and the application ends as a boundary or mixed lubrication phase, where there is some asperity contact, shown by and that's shown by polished track appearance. If you get the bearing apart and you look at the raceways and you look at it polished, that may well mean that the viscosity is the kappa rather is less than 1. And the rate, and that does compromise the life rating. So the aim should really be to achieve kappa of between 1 and 4. So that's in that sort of area around about there. And that's where we're getting full EHL. So we know what a separating oil film is, but how thick is it? The answer is between 0.1 and 1 micron. Very, very small, as you'd expect. 0.1 and 1 micron. Now, as a honed and polished finish of an SKF bearing is about 0.2 of a micron. A 0.1 micron oil film thickness would only achieve boundary lubrication. EHL is only really achieved at about 0.5 of a micron to 1. About 0.5 a micron really. 1 micron would be a very high kappa value indeed, so you're really achieving quite good if you could measure it, but 1 micron you'd be doing very, very well. Apparent from this is the fact that you should never compromise on bearing quality in terms of rolling track finish. Even if you can't get an SKF Explorer bearing, at least ensure you are using another quality brand. Equally apparent is the danger a large, hard and sharp grinding or welding particle, about 20 times larger than the thickness of the grease film, would have on the bearing. And that shows what happens. Such a particle tends to fragment as it's drawn into the rolling path and overrolled to seed potential stress razors, which could become the source of future fatigue spalls. Dirt particles such as these may therefore have a reductive effect on the calculated fatigue life of the bearing. However, on the positive side, awareness of contamination may also enable steps to be taken via improved cleanliness, maintenance, and oil filtration to improve the bearing fatigue life. Analysis of particle size, hardness, and type, and of course probability of such particles entering the bearing load zone, has in recent years led to the development of advanced life calculation models. Up to now, we've been discussing oil, not grease. However, grease is merely like a sponge releasing oil over a period of time. These points are therefore equally applicable to both. The vast majority of grease composition is oil, sometimes up to 95%, and can be a mineral, synthetic, animal, or vegetable oil. The thickener tends to be a soap, skeleton, such as lithium, calcium, or sodium, and then additives for improving properties such as anti-corrosion, antioxidants, and extreme pressure and stroke or anti-wear, such as phosphorus, sulfurs, or chlorides, and solids such as molybdenum disulfide, never say that, ceramic powders, teflons, or graphites. Now, different oils and thickeners are not necessarily compatible with each other. Compatibility is indicated in this table for many of those different components, so care must be taken to ensure that incompatible greases are not mixed. Organisation is obviously the key. So, oil or grease, which one do we want for any particular application? Some 80% of all applications do use grease. The advantages are self-evident. Grease generally means simple seals. These are some of the seals shown in our Seal for Life degroupable bearings, to retain the grease rather than complicated ones to retain oil. This is particularly important in vertical applications. Oil needs to be monitored to ensure correct levels and quantity to enter the bearing. Not the case with grease, which with automatic dispensers is generally maintenance free. So, nice and easy. Even in challenging dirty applications, grease is often used to purge contaminants away from the bearing. Maintenance free being increasingly important, more and more designs are being made for grease lubrication. So oil is increasingly being used at the extreme margins where grease is not so effective, where a flow is required to reduce temperature, for instance, or for large bearings moving at speed, or in gearboxes where the oil lubricates the gears also. The right grease. It is important to understand there are certainly hundreds of, or perhaps thousands of different types of greases. We alone in SKF have about 20 different types of greases with specific properties and characteristics in our portfolio. And of course, there are many more grease manufacturers and suppliers with an even broader range of different greases. Making the right choice of the best suitable grease for your application is therefore quite complicated. The right grease depends on many factors, such as the type of bearing, the speed, operating and ambient temperature, size and type of load, application setup, horizontal or vertical is important, and of course also requirements when it comes to food safety, biodegradability and chemical resistance. Another important feature of grease selection is consistency. Grease consistency depends on type and quantity of soap, the viscosity of the oil, and many different types of factors. A grease can be hard, like a wax, or very soft, like a thick oil. A grease consistency class is indicated according to the NLGI index, where NLGI, that's another tongue twister, NLGI stands for National Lubrication Grease Institute. There are 9 classes in the NLGI index, but only 3 are generally used for rolling element bearings. The standard choice tends to be a number 2, as you can see. But with large bearings, high ambient temperatures, vertical shaft, and above normal vibrations, a consistency 3 would be a better choice because it's a bit stiffer. These types of applications will require a thicker and more stable grease than normal. However, at low temperatures, oscillating hinges, not fully rotating movements, and with central lubrication systems, a slightly softer number 1, where the oil needs help to bleed or sweat. I prefer the term sweat actually, out of the thickener. An NLGI consistency 1 is preferred. So I think you can see that. So the softer greases is like butter. So in fact, butter is a very good analogy. When you take butter straight out of the fridge, it's hard as anything. Leave it out for a while, it softens due to temperature, and that's just temperature doing its work, reducing not only the viscosity but also the consistency. Consistency is determined with a consistency meter shown. At lab temperatures of 25 degrees centigrade, we leave a cone with a certain weight for 5 seconds in a jar of grease, and the number of tenths of a millimetre the cone penetrates the grease pot will link to the NLGI consistency table. So that's what all those numbers mean. Go down from 475 down to about 85, and that's just the number of tenths of a millimetre that the grease deforms in that test. Now, a correct way of lubricating. The initial lubrication should usually follow the assembly and adjustment. The bearing should have 100% fill, except for carb, which only requires about 50%. But I won't go into the reasons why that. If you're interested, just drop me a line. Apply on one side of the bearing until it is seen emerging from the other side. Use gloves and suitable tools to prevent contact with the body. Then apply grease into the free space on both sides of the bearing. The quantity depends on the speed. Normally, it will be 40 to 50% of the free space. However, for high speeds, now definition of high speeds is more than 70% of either the reference or limiting speed specified in the catalogue, whichever is the lowest for the relevant bearing. We fill the grease space up to 20%. Yeah, so in that case, we fill the grease free space up to 20% because too much grease can be damaging. At low revs, which is less than 20% of the reference or limiting speed, whichever is the lowest, we fill the grease space maximum 90%, so we almost fully pack it, because at that sort of low speed, we're safe to do so. Know that too much grease can cause overheating, and with early bearing failure as a result, but of course also a potential fire hazard with all the consequences of it. After proper lubrication, the bearing system's closed out from the outside world as quickly as possible by placing the cover and seals and providing the seals with initial lubrication and a dollop of grease. Relubrication of bearings. Like the grease selection, the relubrication interval is a function of bearing size, type, speed, temperature, and load, but also shaft orientation, horizontal or vertical. With this information, the relubrication interval may be calculated in operating hours. The quantity of relubrication can be calculated in grams from the size of the bearing and method of lubricating it. It is very important to ensure that lubrication is provided through the bearing and where the old and stroke or excess grease can be removed from the bearing system when relubricating your application. After all, too much grease causes overheating and premature failure, and therefore extra costs, and is also harmful to the environment, of course. We often see too much lubrication where grease is continuously pumped into a dead end on the expectation that is going somewhere important. Now, how often does someone shout, "Help! That motor gets so hot and I've already lubricated it a little extra"? Note the sealed bearings. These cannot be lubricated and should not be relubricated. Or this example, look at the grease nipple and the excess grease. You can bet that the bearing does not get lubrication. And on this example, we could have used a lubrication groove in the bearing to lubricate. So if it's a spherical roller bearing, it does have that lubrication groove, which is very handy. So always look into the possibility of using that. Not always possible, but definitely worth checking. Lubrication management. Consider a detailed lubrication management program. Consider a hand or automatic lubrication method. Think about the right tools and equipment, availability of qualified personnel and lubrication technicians. Work with lubrication schedules and lubrication routes. Think of condition monitoring, inspection of your rotating equipment, applications with equipment and sensors. Also have sufficient care for your lubricants. Take care of lubricants. Remember the dangers of mixing incompatible greases and the need for organisation. Also, the availability of the right lubricant and care for storage and stock, for example. Considering the environment in cases of leaky packaging, and also storage time and shelf life of lubricants. Also ensure careful inspection before using your lubricants. Take care of new, clean packaging, ensure clean and professional tools. Provide protective gloves. Many people have allergic reactions when coming into contact with industrial lubricants, so also make sure that the material safety sheet, MSDS, are available in red. Also, very importantly, make sure the proper disposal of lubricants, used or not. Think again about the environment. This is a selection of the SKF grease selection table. This can be found in the Mapro catalogue and on our website. However, due to the complexity, our advice is to consult our application engineers, and they can help you make the best lubrication choice for your specific application. They are the primary technology experts. And again, think about the 36% premature bearing loss that is due to incorrect lubrication. We're also happy to support you with the right tools to carry out lubrication in the most optimal, environmentally friendly and safe way. Our authorised SKF distributors are happy to help you select the most suitable tools for your work. Good tools are half the work and will reward you by making your application run more reliably and therefore longer. Also, on our SKF website, www.skf.com, /support/engineering tools. There are programs available including SKF Lubrication Planner, which is a lubrication planning program, SKF Dial Set program that can help you determine the correct lubrication interval and lubrication for different automatic lubrication systems, and SKF Lube Select. Which, as the name implies, is a program that can help you choose the right lubricant for your application. However, the program does not take into account all the details of your specific application and chooses from a limited number of greases that have been tested by SKF. Of course, you remain responsible for your choice of lubricant, so please consult the applications engineers to make the right selection choice. For the right knowledge to be able to make the right choice, we're very happy to recommend our SKF lubrication training. After following this one-day training, the lubricant technician should be able to make the right lubricant choice, thus significantly extending the life of your bearings and improving the reliability of your applications. The lubrication technician will also be more aware of lubrication in the right way and be more motivated to carry out the work safely for yourself and the environment. For more information about our training courses, see our website or send an email to training.uk@skf.com. And we can further discuss your needs for a suitable training course either at your own location or at one of our SKF locations in the UK. If you'd like a webinar where we can fine-tune the content you're liking, then we can respond directly to questions from yourself or your colleagues. Please send an email and we will contact you. Before I go, I shall leave you this summary here for a little while for you to take notes as necessary. So any questions related to this webinar, email me on chris.monday, that's my name, @skf.com. Training course inquiries, use training.uk@skf.com. And please note the regional sales manager for your area from this map, and feel free to contact them for any commercial inquiries. So thanks to them.